the GUI MIT joint program. And ever since, I think, well, I don't know if you did on the way, but he graduated in Caltech and was promoted there. And he is now a professor in Caltech, and he will tell you the story about calcium carbonate dissolution and concentration in the ocean.
Thank you, everyone, for coming. I apologize that I'm not in the best of health. This is about as loud as I get. Can you guys back there hear me? That looks like Dan is actually saying yes, so that's the promise. This is, even though I don't look it right now, I'm actually quite excited about this bit of work that's been going on in my group, and jointly with Will Burleson at USC. And also, Jonathan, his fingerprints are all over this work. It's actually stuff we started together. There's pieces that have continued together, pieces that have diverged. Okay, can you go down a little bit?
I will do it.
Or I can just pull the whole thing forward. So I think some of you might know Adam Sabas, who spent a couple of long stints in Iran, cultivating some of the foraminifera and corals that we then promptly dissolved after, as soon as he grew them. That was sort of the point. And I gave a version of this talk that is a little bit different, so those of you that were at the device a couple days ago, a lot will be the same, but then I figured this is geochemistry central in Israel, so I've put a bunch more of the sort of geochemical parts into the talk. The first point about why you might want to care about carbonate dissolution in the ocean has really to do with the alkalinity budget. There's several ways to motivate this part. But without worrying too much about the details of alkalinity, if we just say that it is the result of acid waters landing on basic rocks, extracting cations of those rocks, and then flowing down and starting to fill up the ocean, we'll call all of that one unit of alkalinity coming into the ocean, one unit of flux coming into the ocean. Well, then at steady state, the alkalinity in the ocean can't be going up or going down. It has to be found some sort of constant value. And so that's great. Thanks. I appreciate that. So there must also be one unit of alkalinity coming out of the ocean at this same steady state. That is chiefly by the burial of calcium carbonate, is the carrier of that alkalinity. Sensu vents a little bit in off-axis low temperature interactions. They're a small part of the alkalinity budget of the ocean, but really the bulk of it is done here as calcium carbonate. But no calcium carbonate in the ocean that is landing on the seafloor is actually just inorganic precipitation. All of it is biologically mediated. And all these crazy communities in the surface ocean don't really care about this alkalinity balance of the ocean on the timescales at which they actually make their shells. They care, the corals and the forams and the coccoliths, they care about temperature and light and predation and nutrient supply. And so they overproduce calcium carbonate by a factor of 4 compared to what needs to actually be buried. So this sets up the basic problem of carbonate dissolution in the ocean. 3/4 of every shell made in the ocean must dissolve somewhere. And we're not actually very good at understanding where or even why. Which seemed to me and Will to be like extremely embarrassing that we would be doing this problem for so long in chemical oceanography. And so much of the motivation of getting started in this work was about trying to understand how is it that this happens, that these 3 arrows come back at you. Of course, there are several other ways you could motivate this, and one of the chief ones is that this cycle of buffering of alkalinity in the ocean and discrete dissolution of alkalinity produced on the surface is an important part of our records of atmospheric CO2 over glacial cycles. You can't explain this whole glacial and glacial amplitude of 80 to 100 per mil. I'm sort of assuming that you guys know about this is an ice core record, the temperature down below, 800,000 years on the x-axis, and the up and downs of CO2 going along with glacial states. every idea that's ever come up with to explain this atmospheric CO2 change also must invoke carbonate compensation, must invoke these buffering by that alkalinity cycle in the ocean. In addition, we've gone hog wild with this, right, in the Industrial Revolution, and now we're well over 400 ppm, so it's literally kind of above where the tip of this arrow is. We've placed a massive perturbation on the system of increasing the CO2, and we'd like to understand what to do about that. And that's the second half of this talk, maybe more like the last 10 or 15%, is an engineering way forward. We might be able to do something based on some of the discoveries that we've come up with from the geochemical investigations. One of the nice things about being a geochemist is we know what's going to happen to that big red arrow that's shooting up there. Because this is what volcanoes do, right? This is the cycling of CO2 on Earth between the ocean atmosphere system and the interior of the Earth. And the basic reason that we're not Venus, right, that we didn't take all of our CO2 and just have it completely accumulate in the atmosphere and lose the trickle point of water, is because of this buffering reaction, that calcium carbonate sediments react with the excess CO2 to form bicarbonate and calcium. The problem, and the reason you don't hear about that as a way forward to solve global warming, is the timescales are too long. They're very short geologically. It's a very nice rapid response buffering system. But if you were to say, this is nice work from David Archer in the 90s, if you do like burn a bunch of fossil fuels, say, and raise up atmospheric CO2, God forbid, to 2,000 ppm, and then ask a geochemical model what will happen in the ocean atmosphere system for that, gradually the CO2 will come down as Pacific carbonate ion concentration will drop, the inventory of calcium carbonate in the upper ocean sediments will go down because it's reacting with the CO2, and overall the whole system will actually come back to a steady state in tens of thousands of years. The E-folding time for this is about 6,000 years. Okay. The reason that this takes so long is severalfold. There's the air-sea gas exchange, which is relatively short. There's the overturning time scale of the ocean to get the CO2 down to these sediments. That's a 1,000-year sort of time scale. The reaction rate itself is relatively slow, and then you also have to have bioturbation. You need to bring worms, you need to stir up more, so you should dissolve the surface layer. Worms have to stir more up. All of these go into it. And unfortunately, our understanding of the dissolution rate itself is somewhat embarrassing, how little we know about it. So here's a really beautiful example of some excellent work on this problem in the mid-60s. This is Peterson's famous balls experiment, or spheres experiment. And this is deploying a bunch of polished calcite spheres on a mooring that is the full water column mooring. So he took these little round balls, weighed them ahead of time, put them out at sea for 3 or 4 months, came back, picked them up again, and weighed them again. It's like, beautiful, of course that should work, right? Like, what a great way to measure dissolution. Weight, right? And he found this really beautiful signal south of Hawaii in the Pacific, that he saw the onset of a slight tick up in the amount of weight loss of the calcium carbonate, so a slight tick up in dissolution, shallow in the water column, and then this big rapid rise deeper down, and he noticed that this was the same place that the calcium carbonate content of the sediments dropped off to zero. He sort of said, excellent, drop the mic, right? We got that worked out. But no one has ever really well explained why this happens in the water column. Why is it that you get so much faster, deeper? Okay. Since Peterson, there's been all sorts of different flavors of work on this problem. And here are a variety of rate laws for how the dissolution rate of calcium carbonate works. So this y-axis is dissolution rate in percent per day. And the x-axis is 1 minus omega, where omega is just the saturation state. Where do you sit for calcium and carbonate ion relative to the equilibrium constant? And so if omega is greater than 1, you tend to precipitate. If omega is less than 1, you tend to dissolve. And so this is 5% undersaturated, 10%, 15%, equilibrium sits down over here. And what is not immediately obvious from these curves, but people have essentially done this as an empirical curve fit in oceanography. And they say the rate is proportional to the thermodynamic driving force. Anybody who works on kinetics is already nervous, right? It's very rare that thermodynamics is a good explanation for the kinetics of a system. And that proportionality has a rate constant, and then what the heck, let's raise it to an exponent also while we're at it. That exponent of rate laws in the literature ranges from 1 to 4.5, and k ranges over 3 orders of magnitude, which is really a statement of ignorance, right? We really don't understand this system at all. In fact, it's even worse. If you take now the log rate over here versus the log of 1 minus omega, those are all curve fits to data that exist out over here, various flavors of data, some in freshwater, some in seawater. Here's where the ocean sits, right, in this big blue area. All of the work that's been done is essentially outside of the range of the ocean, except for Peterson, who actually tried to put the balls out in into the water column. And so these huge differences, these orders of magnitude difference in the rate dependence, are extrapolations through the key region that we care about. Okay, so Will and I decided that that was embarrassing and thought, how do we get to work on this? And one of the really nice things about being at Caltech is that folks are really not afraid of isotope labeling. And there's sort of a longer story here that I'd be happy to tell folks at some other time. But we hit upon the idea of monitoring dissolution by taking purely labeled calcium carbonates, calcium carbonates with pure C13 in them, put them inside a gas impermeable bag. Turns out not all bags that are labeled gas impermeable actually are. That was like a year's worth of work. And then change the saturation state, fill the bag with seawater with no headspace, change the saturation state just by adding a little bit of acid in. And we built a special port that allowed us to sample the bag over time, take out little bits of water as we go. And that then let us measure the accumulation of C13 in the dissolved form inside the bag over time, just by measuring the C13 C12 ratio of TIC, something that we know how to do quite well. And so it's a direct measurement of the mass transfer of carbon from the solid into the bag. So we had to go get a bunch of labeled calcium carbonate. You can just buy it from Aldrich if you like, or we started to grow our own in the lab. We wanted to get different grain sizes. Sometimes we made vaterite when we did it. And then the roughness of the surface, that's going to be an important part of the whole story that we talked about here. We also did the way that we started working with Jonathan. Of course, I should say, many of you probably know this, this is a type of approach to doing this is entirely inspired by Jonathan. Jonathan did this first by labeling carbonates growing forams in C14 labeled solutions, putting them out at sea during geosex, I think it was, wasn't it, Jonathan? Yeah. And then looking at the accumulation of radiocarbon inside whiskey bottles. I was really enamored with this when he was showing it to me on our previous visit here to Hebrew. And Jonathan encouraged me to sort of keep doing this work, and I said, there's no way I can work with labeled radiocarbon. And I work on natural radiocarbon levels in corals and these glacial timescales. And he said, oh, that's not that hard. I said, Jonathan, there's no way I'm letting tracer into my lab. He said, yeah, you're a chicken. You, like young scientist, you don't have a spine, was basically what he was telling me, which is maybe true. And a few years later, we stumbled onto this C13 idea. Okay, so the basic workflow is you take the pure calcium carbonate, you put it in these bags, we do it on shaker tables so that we're not transport limited, then we're really looking at the reaction rate at the surface. You sample the bags over time. Carl has turned out to be a real godsend on this. We thought we were going to have to do this by mass spectrometry, but we've had a really high throughput to be able to measure it by cavity ring count spectroscopy. That comes down to a little bit of just analytically, where do we sit? We've gotten pretty good at measuring the total carbon and the alkalinity of our water. These are the two things we need to know what the omega is, to know what the saturation state is. Overall, we can measure saturation state to 0.01 or 0.02. And then the delta C13 we measure to about 0.1. which is really helpful because with these purely labeled solids, in a 300 milliliter to 500 milliliters of water in a bag, a 20 per mil change inside the bag is 1 alkalinity unit change. Right? That's within the error of everybody's ability to be able to measure it. So if you compare us to the ways of doing this of tracing alkalinity or even tracing calcium accumulation in the bag, we're 200 times more sensitive in that approach. And that's been really what's opened up the whole field, is that sensitivity. What we do then is measure the delta C13 of DIC over time here. It's over the course of several days to a week. You convert that into the number of moles dissolved. These are 4 different bags. Each, this is close to equilibrium and further away from equilibrium. And the slope here, these linear slopes, is the rate of dissolution. This is the amount of carbon you're adding per unit time. The curvature down here is actually really interesting. I'm not going to talk about it very much, but I'd be happy to tell you more about it at some other point. Okay, that then means that we can, on the same sort of plot that I was showing before, here's the beginnings of our new data, really starting to extend quite close to equilibrium, right? Getting measurements within the range of seawater and trying to get a grip on what's going on with this dissolution rate. The first order answer to these are some of the early measurements was that here's rate versus 1 minus omega for 3 different grain sizes. And then here is normalizing those same rates to their surface area rather than to their weight. And they all fall onto the same curve. And the answer is you're very strongly curved. In this curve, in this n world, k times 1 minus omega to the n is much bigger than 1. Right? Then there's the strong curvature in this empirical way of flowing. All right. So now that you're armed with this new tool, right, and this ability to make measurements close to equilibrium, what are we going to do? Like, what problems could we try to go out and solve? And I'm going to show you a fair bit of what we've been learning about the physical chemistry and the sort of fundamental geochemistry of how it is these surfaces are dissolving. This has turned out to be a really fun story. There's a neat evolving story about how it feeds back into the chemical oceanography and the alkalinity cycle itself. And then it's also inspired us to start thinking about how we might do ocean alkalization at scale, like how we might do this dissolution rate fast enough to keep up with human emissions. Okay, so digging into the chemistry of the dissolution itself. Why might you want it to be linear in the first place? Like, where did that idea even come from besides our just love of fitting things to a straight line, right? And there's actually good chemical kinetic reasons to justify why the rate might have been linear in the first place. So here is a funny looking reaction, right? This is the same data we had before. Calcium carbonate plus water goes to calcium plus carbonate ion plus water, right? It seems ridiculous. I just put water in each side. This is how to start thinking about things chemically, kinetically rather than thermodynamically, right? This is saying water attacks the surface of the calcium carbonate, liberating a unit cell as a calcium and carbonate ion solution, and regenerating the water as it goes. One way to think about this is water is a source of a proton to the surface of the calcium carbonate to have an acid-base reaction happen right at the surface. Okay, so this is a statement of a possible elementary rate law. This is how the chemical kinetics works. You write down an idea about the actual path, right? This is the difference between thermodynamics and kinetics. So kinetics is totally path dependent, thermodynamics is not. So if you say that the path is going through water attack at the surface, you can write out 2 statements of just truth. Thermodynamics still has to be true. KSP is equal to the ion product divided by the activity of the solid here, also equal to the forward and reverse rate constant ratio. And you can write out a generic rate statement. The net rate is equal to the forward rate minus the reverse rate. This is gross dissolution, this is gross precipitation. The difference between the two is the net rate. Well, you can just do a little bit of algebra here, and you get to rate is equal to k times 1 minus omega, and n must be 1 in this particular case, right? If you just substitute in these expressions into this equation. that makes a really interesting prediction, right? It says that the gross dissolution rate should be independent of solution composition. The gross dissolution rate, not the net, the gross dissolution rate. As long as the activity of the solid is 1. As long as this funny curly bracket term here, the activity of the solid itself, is 1, the classic thing we always tell ourselves when we start to write out chemical equations of solids and solutions interacting, I don't want to have to deal with all that funny activity of the surface. Turns out we have to deal with it, and we're going to for the next half an hour or so. Okay, but there's a good justification of why you want to have n equals 1. And in fact, the literature supported this, at least in freshwater. So here is log of dissolution rate versus 1 minus omega for one version of many that are out there of the dependence of dissolution of calcium carbonate, not in seawater, but in freshwater, has a slope of 1 on this diagram, which is the same as that exponent of 1b. Seawater, on the other hand, right, if you're only ever measuring out here far from equilibrium, you might feel like, great, that sort of looks the same. And as we get our data that comes in close to equilibrium, there's several orders of magnitude difference here in what's going on, and you have this funny curvature in here. This is very much not n equals 1. I already showed you this. This is kind of the same data that I was showing you before. But this is why the field was sort of wanting to fit things sort of towards 1 in the first place. So we're going to have to try to understand that, why are freshwater and seawater so different from each other, or are they? It turns out, I think they're not. Okay, well, if you're going to try to solve this and think about how it actually works at the angstrom scale, how it works at the surface of the solid, you're going to have to consider several flavors of chemistry that are going on, several flavors of the energetics of the environment of what's happening. The first point is that it's not just some flat surface, right, or some sphere of calcium carbonate. There is a very important energetic landscape to the surface of the solid itself. And there are very different ways of being able to actually pluck out individual unit cells here. So for building up calcium carbonate out of these unit cells, I could dissolve it by having step edge retreat. Right? That's the close to equilibrium mechanism. That's the lowest energy one. As I became more and more undersaturated in this solution, I can start to activate a mechanism that plucks out etch pits, right? Plucks out individual unit cells. I first would do it near defects, where there's already a lattice strain in the solid to begin with. And then ultimately, if I got really undersaturated, I could begin to do homogeneous edge pit dissolution. This is a surface energetic approach to thinking about how dissolution works. It's actually quite popular in geochemistry right now, mostly due to the advent of AFM, atomic force microscopy. You can actually go measure these surfaces retreating and measure, and I'm going to show you data like that for our system. However, that approach, which is dominating a lot of the weathering studies and mineral dissolution studies that you go see in Goldsmith these days, that approach, in its purest form, completely ignores that there might be any aqueous chemistry that matters. Right? The only reason that you care about calcium carbonate ion in that approach is how it sets omega. What is the potential energy that I have from my solution to go drive any of these surface mechanisms? And seawater, this is kind of a mess. So if I think about how calcium and carbonate move on and off of this solid at individual places, then it's the interaction of their free calcium and free carbonate ion that matter. But of course, in seawater, 90% of the carbonate ion is actually complexed by magnesium, right? As this aqueous complex, magnesium carbonate 0. Calcium is complexed by bicarbonate, right? The activity of carbonate ion is not the same thing as the total concentration of carbonate ion that's out there. And the same thing is true of the surfaces themselves, right? These little tents here, this is carbonate bound to the surface, carbonate ion, or calcium bound to the surface, but they also can be complexed by magnesium or by protons or by water, right? The activity of the solid is not just free calcium and free carbonate sticking off. All right, so we're going to have to worry about both the aqueous chemistry side and the surface energetic side. Well, the freshwater folks really had this all kind of solved very beautifully in the mid-90s in a great summary paper by Harakaki and Bucci. And they proposed, and this proposal worked out very nicely, that there are three elementary reactions that matter. They were not considering the surface energetics part at all. They were just doing it as aqueous chemists. They said that this first one I already showed you, water attack of the solid, leads to aqueous calcium carbonate dissolving. This is calcium bound to the surface with one of its two charges delocalized into the interior. That's why it's calcium +1. So that little sign just means touch it, attached to the surface, literally bonded to the surface. But attacked here by carbonic acid to then dissolve, or carbon ion slates could be attacked by protons. 3 different ways of getting acid to the surface to dissolve. And if you go and try and use these 3 elementary reactions to fit the existing data, so the measured data are these closed symbols. It's a summary of a lot of data from a bunch of different folks. Using this elementary, 3 elementary reactions, here's the rate that they calculate in the squares. They lie on top of each other kind of nicely. But a really nice part about this is you can divide it out into its various terms for these different ones. Here's the net rate coming out. This is the gross precipitation term, and this is the gross dissolution term, having no dependence on the saturation state, just as you would predict, right, that, as we pointed out earlier. And all of the curvature that you're getting in the rate dependence on omega is coming from the back precipitation term. Works out beautifully, right? However, these are going to be trouble in seawater, right? The surface speciation is likely to be very different. Arakaki and Mucci could not solve this problem until Van Kaplan read his thesis, just in the early 90s, where he, for the first time, worked out the surface speciation of calcite in freshwater. What's the activity of the free carbonate ion and the activity of the free calcium compared to the complex ones? It was only with his model that this elementary rate bond came together, and in seawater, this is going to be completely different, and not actually very well understood until recently. Okay. Of course, surfaces are also probably going to matter. We can't be like Arakaki and Mucci and just ignore the surface energetic landscape. We know from atomic force microscopy or from interferometry measurements like these down here. This is an hour-and-a-half time dependence. Like you're used to. You guys see that this is a little peninsula sticking off with a sharp point here. And then as the AFM, as you have your carbonate sitting in water and the AFM making measurements, it's getting more and more rounded and retreating back. That's step edge retreat being measured in real time here by the atomic force microscopy. This is 1 unit cell step down, right? This is an angstrom level measurement. Same idea here, that the surface landscape is actually quite complicated. You have etch pits forming right in the surface, and you have defects in the solid that can be important sites of dissolution as well. And so we're going to have to consider both of these simultaneously. There was a real breakthrough in this approach of how to apply AFM-like measurements back into theory of dissolution by Patricia Dove. There were a few folks who were dancing around this. She basically took the ideas that came from ion by ion growth coming out of the early work in the 50s of how you precipitate calcium carbonate and flipped it on its head to look at it for dissolution. In her case, a dissolution of quartz. Unbelievably boring, right? Who wants to do the dissolution of quartz? I mean, first of all, you're sitting there a long time waiting for the quartz to dissolve. It's not very soluble. But Patricia turned it into this fantastically interesting subject with this ridiculously complicated looking result, right, that comes out of the rate. What's going on here, however, is a description of how it is that dissolution by etch pits, either homogeneously or at defects, should work. She then continued to derive the theory here for pre-existing steps, an even more complicated looking thing. This is actually not as bad as it looks. The gray things are all stuff that you know ahead of time, okay? So that's omega. Sigma is just another rephrasing of omega. This is the height. This is the height of a unit step right here. This is the equilibrium constant. This is the unit cell volume, so on and so forth. A is the spacing. The three really sort of fitting parameters and the three fundamental parameters that are involved in any surface energetic term. And by the way, this over here on this side is just the rate normalized to in this funny way to saturation. Our alpha, that's the energetic barrier, the kinetic energetic barrier to actually being able to jump over and get towards the products. Right? So this is alpha in this case is for edge-pit formation. Beta is the fundamental rate at which a step retreats, at which it moves back. And NS is the frequency that these appear on the surface. Okay, so the three things that you actually need to know from a theory like this are the kinetic barrier as an energetic term, beta and NS. All right. So the nice thing about this theory is it makes a pretty strong prediction of what your rate versus saturation state in this funny normalized space should actually look like. Homogeneous edge pit to solution will be linear. Defect assisted will also be linear, but at a shallower slope. And there will be a key omega critical where you transition from one to the other, being the dominant dissolution mechanism. And then step edge retreat is actually curved in this funny normalized space. It's not that you're actually getting faster as you go towards equilibrium. It just has to do with the denominator getting very small. But the three different mechanisms that are available to do dissolution fall out very beautifully, and she showed this nicely for quartz dissolution. Okay. Well, we had been going after this problem and thinking about the temperature dependence of calcium carbonate dissolution. And so here's rate versus 1 minus omega on a log plot. And we'd already begun to notice that the reason it's curved is because it's actually three different straight lines. It's very hard to get points out here very close to equilibrium to get the slowest one of the straight lines. But this curve, right, this n being 4, 3.9, or 4.5, whatever you want, is just an artifact of trying to fit a single rate law to what looks like three different mechanisms. What's going on? So we were quite excited to find Patricia's work and said, great, let's take our data and cast it into that same space. And so this is literally the same data, but now in that Patricia Dove space, and you can see at every temperature, here's homogeneous edge pit dissolution. And it transitions to defect assisted edge pit dissolution. And then occasionally we get a data point close enough to equilibrium that it transitions to step edge retreat. And these omega criticals are staying constant across the temperatures. The temperature is not the thing that's actually changing when you cross omega critical. If you have data like that, it lets you then actually start to go dig out these numbers. And so I won't dwell on this for too long, but if you take the slopes of these fits, right, go back and just ask, okay, we measured this slope, that slope is equal to this term right here, from which we know everything except alpha. And so you can ask, what should be the temperature dependence, these are different alphas across a range of temperatures, what should be the temperature dependence of alpha if this theory is right? Right? Just what should the slope be like? And indeed, for homogeneous edge pit dissolution, our data falls nicely along an alpha of about 35 millijoules per meter squared. But for defect assisted, it does not, right? Our data doesn't fit the theory very well. So when you're just dealing with the edge pits coming out, it looks pretty good. But seawater is looking more complicated than just being able to do it as the freshwater story, which is just the surface energetic form. Okay, we realized that we were going to have to be able to try to get these two communities to talk to each other, the aqueous community and this surface energetic one, that we're going to have to meet them on their own ground and make some AFM measurements in seawater itself. That seems straightforward enough, right? So you get access to an AFM. There are more and more of them around. We partnered with a group at USC, and you get a piece of calcite, and all that they do in the freshwater ones is you put a little drop of freshwater on there, and you bring your AFM probe in that's sensitively monitored as it's going up and down by a laser bouncing off the top of it, and you measure your surface. And you can measure it in real time. The problem for us is that this seawater droplet will constantly be exchanging CO2 in the headspace and therefore changing the omega over the course of the experiment. In our bag experiments, we had a totally closed system. We knew exactly what our omega was. Here, it's going to evolve over time, right? Not nearly as much of a problem for the freshwater one, but a huge problem for us in seawater. And so the key was to flood this headspace with a controlled CO2 atmosphere that was the right one, that the net flux across here was 0. That took a while to figure that out, but that enabled us to make the very first AFM measurements in seawater. So here are some examples of them. Omega 0.88, where you're largely dominated by the step edge retreat. Here is half an hour worth of measurements, one of these sharp points getting duller as you go. That's a direct measurement of the step edge retreat as you go. Bring yourself down to omega 0.5. This white is just poor image quality. I should say, I'm sorry, the grayscale is height. Here, 1 nanometer above and 1 nanometer below. So this is overall 2 nanometer full scale height as you move across here. And this white is noise, but you can see these black arrows are another step edge retreating, but the yellow arrows are edge pits opening up on the surface. So go make a lot of measurements like this, and we can go look at the edge pit density, right, one of those important terms in the Dove framework, versus 1 minus omega. And our seawater data here is in these sort of bluish circles, and we found no edge pits really that we could see coming on from from omega of about 0.1 to the left. That is the thing, and these spots here are our omega criticals from our solution work, right? This is the transition from step edge retreat to defect assisted edge bits, and this is the transition from defect assisted to homogeneous. And indeed, the AFM shows that you have an onset of an increase of edge bit density up through the defect assisted, and then you get a constant one when you go to the homogeneous. Really beautiful confirmation that we're seeing the same thing on the surface side as we're seeing in the bags. That was a good day. And it's making us feel like we're onto it. Like, we're really like beginning to understand how this system works. The main reason that we're so different from freshwater is because freshwater has very different omega criticals. Almost the whole range of all the freshwater data that's out there in the literature is in the defect-assisted regime. And this is why you could actually do the aqueous chemistry approach, right? To just do, because you're only having one mode of surface dissolution over the entire range of omegas. They didn't make very many measurements down here. This is omega critical of 0.0007, right? To transition from defect-assisted to homogeneous edge pit. There's something very, very different about the physical chemistry of seawater to enable your ability to pluck edge pits to the surface, and that has to be about the aqueous speciation. As chemists are sort of seeing, it's not just a world for physicists. Okay, here's a really wonderful example, I think, of just how you have to pay attention to the aqueous speciation of the seawater. Because we have these bag experiments going on in the lab, we can manipulate. We don't have to just use seawater. We can build our own seawater and leave things out. We can change the magnesium-calcium ratio. We can change the sulfate concentration, right? And so we've started down that road now that we think we really know how to observe this space and explore this space. Here's an example of the sulfate. So regular seawater is here in the X's. Seawater with half its amount of sulfate and sulfate-free seawater here in the open circles. For a range, here omega 1 minus omega 0.3 all the way out to 1. So very far from the equilibrium over here, coming close to the equilibrium over here. Well known in the literature, right? People have these sorts of statements all the time that sulfate is an inhibitor of dissolution. And indeed, when we go to our sulfate-free seawater far from equilibrium, we dissolve faster if we take sulfate out of the seawater. Because Poprosky has actually shown this nicely already they were not seawater solutions. They were medium ionic strength and then adding sulfate and leaving sulfate in. However, we can do better than this. We can come all the way close to equilibrium. So I was just showing you this data blown up over here. But now coming close to equilibrium, sulfate-free seawater is on the other side of the line. Ridiculous, right? Sulfate is both an inhibitor of dissolution and a promoter of dissolution. Close to equilibrium, if you add sulfate, you dissolve faster. Far from equilibrium, if you add sulfate, you dissolve slower. Come on. It's not fair. Well, it turns out you can explain this with the speciation. The surface speciation of calcium carbonate in seawater is not actually all that well constrained. There are a few different groups working on it, mostly because of enhanced oil recovery out of carbonated oil reservoirs. But one thing that has turned out to be true in all of them is that carbonate binds to the surface more strongly than sulfate. Carbonate often does. And so when you're very far from equilibrium and there's not very much carbonate ion, and the other thing that's also true is that so that means that you will dissolve away more slowly if you have lots of carbonate ion. You'll dissolve a little bit less slowly if you instead have all sulfate, but you dissolve the fastest if you had neither, right? If you were able to have just the free speciation at the surface, then that's the fastest way to go. Far from equilibrium, where carbonate ion is low, then the sulfate is the main thing that's taking up free sites, right? And so if I add sulfate to seawater, I dissolve less quickly, I dissolve more slowly. Take sulfate out, and I dissolve faster. But closer to equilibrium, now it's a competition between sulfate and carbonate ion for those surfaces. Carbonate ion has an inherently larger binding constant, but sulfate's orders of magnitude more concentrated, right? And so the sulfate is taking up spots at the surface that would otherwise be done by carbonate ion, such that if you take sulfate out, carbonate ion goes and sticks to those sites instead and slows down dissolution. It flips the sign of the effect of sulfate. Totally cool, right? It's the aqueous chemistry playing a really important role in what's going on. It's actually even cooler. Here is rate versus 1 minus omega, the same data that I was showing you before for regular seawater, half sulfate and zero sulfate. So the zero sulfate are these open circles, and the closed circles are the half. These model fits are the Arakaki and Mucci elementary rate laws, right? Let's ask, maybe freshwater and seawater are doing exactly the same thing, but we need to understand the activity of the solid better, right? That's the difference in the activity of the solid between freshwater and seawater. And indeed, in the regime of defect-assisted extrait formation, so just in this regime in here for seawater, we actually are able to fit quite nicely with the Arakaki and Mucci model, our seawater data. Freshwater and seawater are not all that different, right? Carbonate dissolution is always the same thing. The attack of the surface does have 3 elementary rate laws, but the surface itself is very different looking in seawater than it is in freshwater. That John Navio figured out where he commended his thesis a few months ago. This is brand new, this model right here. We think it's really fun that we're actually beginning to unify these mechanisms. Okay, so we'd like to know something about the system, not just in the lab, but actually out in the ocean itself. And I'm going to show you just a couple slides about this. But inspired by Jonathan, we tried to figure out, could we make these bags work out at sea? The basic idea is to modify a Niskin bottle. So this is a Niskin bottle here, and at the top of it, there's the bottom of it here, there's 2 lids that are going to snap shut, that's now closed. And we attached a pump and a battery pack to it, and drilled 2 holes with these tubes that are going to circulate through this little box. We set up a closed loop circulation system so that whatever we put in this little box, where we're going to put our C13 labeled calcium carbonate, will feel the seawater at whatever depth you trigger your Niskin bottle to shut. So we're going to be able to do in situ incubation, just like we did in the lab. So we went to try to go do this in the North Pacific, occupying stations from Hawaii up to Alaska. We did it because it's a natural reactor for changing omega. This is the calcite saturation. Here you're 25% undersaturated, 20%, 10%, all the way up to an omega of 1, right? And so we just occupied stations along here, hanging our bottles on a wire at different depths and incubating through a gradient of omega naturally out of the ocean. Excellent. Here's what the data looks like. Rate versus 1 minus omega for different stations. And we're getting that same curvature, right? We're seeing those same sorts of rate laws that we saw in bags in the lab. If we do it as log and log, we'll find that we have the same break-off. These clusters of data point are from after a storm came through. That turns out to be important for tossing us off the line. And it's true for aragonite and for coccoliths as well. Right? These are C13 labeled aragonite, C13 labeled coccoliths that we then go and dissolve. It's actually even cooler, right? If we take this data and try to summarize it as log rate versus log of 1 minus omega, here's our lab data at 5 degrees, here in the squares. Here's all the calcite data in the circles from out at sea. Omega critical in the lab and in the ocean are the same. We find the same kink spot. Step edge retreat, close to equilibrium, defect assisted edge pit formation, but a factor of 4 off. It's a factor of 4 slower. That is a whole other interesting story that we think actually has to do with DOC, which is when the storm actually messed up the rate dependence. But I wanted to point out, here's Peterson's data from 1966, recast, right, with better understanding of what omega actually is. Peterson's, the spheres are here in the squares, and they also have the same kink. That big jump that Peterson found was because of this transition from step edge retreat to defect assisted. And it's all within an envelope that we think is largely controlled by things like dissolved organic carbon. It's now pretty well understood, I think, what the rate dependence of calcium carbonate is in seawater, both in the lab and in situ. Okay, I want to take the last 10 minutes here to say something about carbon sequestration. And the reason that we got interested in carbon sequestration is because we stumbled into a catalyst for this dissolution. We were trying to understand these elementary rate laws, right? We were trying to ask the question, how could we individually probe proton attack at the surface? Well, that's pretty easy. You just lower the pH in the seawater a lot, right? Other people have done this also. That's the very far from equilibrium stuff, right? How do you probe carbonic acid attack of the surface? Right? Well, you need to somehow have a way to juice up the carbonic acid activity, right, in seawater and watch to see if your amount of juicing, it then changes the rate. Well, a good way to do that is to use carbonic anhydrase. Carbonic anhydrase is an enzyme that catalyzes this reaction, the hydration of CO2 to become carbonic acid, to bring it close to equilibrium. And so if you're being limited in your dissolution rate by the activity of carbonic acid, there's 700 times more CO2 aqueous in seawater than there's carbonic acid. Putting carbonic anhydrase into the bags would alleviate that rate-limiting carbonic acid and let you go faster. And so we did that. So here's log of dissolution versus 1 minus omega. Here for uncatalyzed seawater, I've showed you curves like this before. And here's for different amounts of carbonic anhydrase added into the bag. It was 500 times faster, close to equilibrium. This is a non-trivial catalysis. Right? Clearly, CA is playing an important role, and we thought we knew what it was. It turns out we were wrong. We thought we knew it was this increase in the activity of carbonic acid. Okay, it's even true far from equilibrium that the CA is a good catalyst. If you have a catalyst for this reaction, you don't have to wait, right, for CO2 to get down to the calcium carbonate at the bottom of the ocean. We'll just go mine the White Cliffs of Dover or go to the limestone quarries in Tuscany and react them with flue gas or ambient air and make saltier water, make that bicarbonate and calcium. What if we try to engineer this whole thing to keep up with emissions? Well, the first thing you might do is write down the scaling law. in order to keep up with 40 gigatons a year of CO2, that's approximately what we've done per year over the last couple of years, you need a limestone block that's 2 miles on each side. Thank God we have Israel. right. We need a limestone. We're coming to you for a bunch of limestone. That all this is a restatement of our energy problem, right? There's nothing inherently wrong with our approach just because it's a big block of limestone. That's how much CO2 we put out, right? It's a little bit like saying, oh, we can't convert to solar because the solar panels will cover the size of Arizona to the U.S.'s energy. No, that's actually the problem we're up against. Right? If you deny that this is not a good solution because of the scale, you have no good solution because the scale is unprecedented that we're trying to deal with to solve our CO2 problem. If you try to do this reaction in a Walmart-sized dissolution factory, right? Because Americans love Walmart, it seemed like a good reference frame. Uncatalyzed, you need 24,000 factories to be working 24/7 all year long to keep up. If we can make it go as fast as we did in the lab, we need 600 factories. There are over 3,000 Walmart superstores in operation in the US today, taking in trucks going out, right? All of the logistics associated with them. That seemed like, wait a minute, that's not that big a number globally distributed. It's 600 more Walmarts to be able to go do this. And so we started really kind of thinking about it more generally. It's kind of a 4-square problem, right? Because you have ambient CO2, really concentrated CO2 coming out of smokestacks at the 3 to 5, even 15% level, depends on what industry you're going interacting with. And you have 2 different fluids you might think about doing this in, seawater and freshwater. Freshwater is great. Omega is already very, very much less than 1, right? So you don't necessarily need the catalyst. And ambient CO2, you might think about backyard streams with a little bubbler going on with limestone sitting there, some highly distributed way. Here, we're actually thinking about how to do this. Couple in power plants and wastewater treatment plants. They're often actually quite close to each other. In Los Angeles, they're literally right next to each other at the end of the runway at LAX. But this is where we're headed. What about seawater and flue gas CO2? Seawater has this problem that it's super saturated, and so you need some of the CO2 to get you acidic in the first place. So we got to work in the lab, and here it is. Here is our little reactor. This is a bottle of seawater with CO2 bubbling into it. This is right here, a little bed of packed limestone that this tube is flowing up from the bottom and out to the top. There's a pump here to push everything along, and an outflow line, which we can either cycle back into the main reservoir or leave in series. And here's what the outflow PCO2 looks like as a function of the flow rate through the system. Uncatalyzed and catalyzed. And so, and then this dashed line is what we would predict. It's not a curve fit. This dashed line is what we would predict given the uncatalyzed rate law I just went through for hours and hours describing to you how we derive that. And so we felt pretty good about ourselves, and indeed, we have lower PCO2 in the water coming out the end of the reactor if you add carbonic anhydrase to the seawater. Another way to think about that is, what's the carbon difference? How much extra carbon is there in the water that's coming out when you have the catalyst, and when you don't have the catalyst? All right, this is a nice little, benchtop demonstration of what some giant thing might need to look like, except the carbonic anhydrase is in the water. And that's not good because it means it's in our outflow also. And it's our far and away the most expensive part of our problem. Let alone, nobody wants us to take a bunch of carbonic anhydrase and start spraying it into the environment everywhere. That would be a terrible idea. Also, we've never worked as a business because it's so expensive in the first place. We have to figure out how to fix the carbonic anhydrase to some sort of solid substrate so it stays inside of the reactor. There are a couple different approaches to that. You can entrap it, or you can covalently bond it. In this case, we're going to do it to glass beads. It's a new branch from the group, right? It's really very much an engineering branch of like, how could we move around this problem? So here is a silica gel polymer that has worked for many other groups, other molecules, to do just the physical entrapment. These are just pictures of what it looks like in the lab. Here's the carbonic anhydrase activity in this 5 units. I'm not even going to begin to try to explain to you what these units are, but just to say that we can measure the activity, and then here is the measured activity versus basically area. If we begin to cut the gel up, indeed, as we expose more surface area of the gel, we are able to express more of the activity. That all seems really great, except it hasn't really worked for us. As soon as we start, we're somewhere between 100 and 1,000 times lower compared to free CA in the activity. We've preserved that activity for a number of days, right? But it's kind of falling off, and this overall looked pretty crappy to us. We've just not been able to physically track the CA very well. But what tends to happen is when those cutting experiments is that the CA is leaking out of the silicon. But in parallel, we were trying to bind it to silica beads. And so here are a whole bunch of different ways that you can have glass. You can have glass wool, you can have silica gel, like yada, yada. This is a terrible way to show data, but I just want to point out that controlled poured glass, so little glass spheres with lots of extra porosity in them, we were able to get sometimes only 20%, but up to 100% of the enzyme that we put into it to bind to it. And we were able to get 80% retention of the activity of the enzyme compared to free. We're starting to feel pretty good about ourselves at this point, right? Here's what the beads all look like in suspension. Here we have put them into mesh bags, because it's going to turn out to be important to separate the beads from the calcium carbonate. And here's what the relative activity, so one is the same as the activity of free CA, looks like free CA versus our beads, looking pretty good. Not only do we get the same activity as free, but we last longer by binding onto the beads than just what fresh CA looks like. Unfortunately, it doesn't actually catalyze the reaction. Here's alkalinity versus time in minutes. Great. There are two reactors set up right next to each other, reactor 1 and reactor 2. At this time, we add beads to one, but not to the other, right? And there's no difference between the two of them. Sounds like a personal problem. So we were worried that it was just a bad reactor, and so we added some free CA, and the alkalinity jumps from that. Problem, AFM told us, is that the CA has to actually be in physical contact with the surface. It's a bummer, but it's true. So here is another AFM experiment. These are not bad images. These are actually clumps of CA together. And when you move the CA away, you can see that the excess activity of the solution is only happening where the enzyme is sticking to the surface. That is, we think, not because, we think that the reason is because the way CA works is it rips a proton off of water, and it takes that hydroxide and reacts it with CO2. The rest of the enzyme is about a proton transfer mechanism to get it away from the active site. And it's those protons that are doing the dissolution. So it's not going to work as a way to enhance dissolution, at least this way, unless you can get CA to always be sticking to the solid as it dissolves and then move to another solid once that one's gone. However, we're not stopping, because it turns out you can do cargo ships without the catalyst. There's so much CO2 in the flue gas of the cargo ship that if you bubble it through seawater, you get acidic enough that the reaction rate is fast enough that if you were carrying a bunch of limestone, they're cargo ships, for God's sake, right? You can titrate all of the CO2 that comes out of the stack while it's crossing the Pacific. And it's just a scaling reaction. I don't know why I haven't done it years beforehand, but that we got onto last spring. The first thing you might worry about is, right? How much volume am I going to have to take up with this limestone, right? Well, we need about 4% of the volume of a large cargo ship. And this is just to point out that the cargo ships coming into LA are all imports are about 8% empty, and leaving LA are about 57% empty. That is the global trade imbalance, writ large, right there. they have lots of extra room to at least do half of the problem, right, on the way back to China. To do this, to carry the limestone. And so we have been writing out models, trying to look at this, and looking at how these models might behave as flow rates. It turns out we need a huge amount of seawater to try to do it. I've been working with a group of ships engineers to think about how this would actually work. The amount of water we need to bring on and off the ship is so large that their pumps really are, it's not a viable pumping problem. But the ship's going at 20 knots. It is its own pump. And so this is a system where the seawater intakes are just holes in the hull. And you flow seawater through your reactor tank. Here's the hopper with calcium carbonate that's bringing in the 3-phase fluidized bed reactor, and then the seawater flows back out. The industry already knows how to do this because this is what they did when they were running by steam rather than running by diesel engines, because they used seawater to cool the water vapor in a closed loop cycle when they were steamers. And so the catalyst has turned out to be a huge amount of work and fun discovery, and ultimately maybe not the best thing going forward. Proton transfer catalysts, however, another way that we're thinking about it. But we haven't stopped because it turns out there's a lot of CO2 in fossil fuel burning, right? Enough to make the ocean acidic. So we're going to give this we're currently working with engineers to try to give this a shot. These are the things I think I just told you. I appreciate you staying an extra few minutes. I'm sorry if I had been healthier, I would have just 10 minutes early.
Yeah. No. Hey, those of you have to leave, can leave, but those who are interested.
Yeah, please, you have to leave.
Jess.
Thank you. Great talk. You really got me excited towards the end. And we've been seeing these, fantastic increases in nighttime dissolution in our coral reef, a lot, also on One Tree Island.
Yeah.
And we've been talking about, these recent findings about increased dissolution in carbonate sediments in response to bacteria. So maybe this may be the answer. Maybe bacteria are producing the carbonic anhydrase and increasing the dissolution rate of carbonates and sediments, and also in our coral reefs.
Yeah, that's a great thought, and one that we have had also. And so one of the things we did on that cruise was measure a section of the carbonic anhydrase activity in particles in the water.
Okay.
And there's plenty of carbonic anhydrase, and it has like a Martin-like fall-off curve, and it's an activity. Mm-hmm. There is carbonic anhydrase activity in the surface sediments as well. Yeah. So the talk that I gave at Weissman showed that there is a lot of dissolution in the water column above the saturation horizon, and we think it is microenvironments on particles where there's a lot of respiration going on, and a lot of carbonic anhydrase in there as well. Yeah, it's really, CA is amazing. Even though I can't get it to scale.
Okay, let's also we give you precipitation.
Yes.
So if it works, therefore the solution, I think phosphate will do also.
So we have checked phosphate. Phosphate doesn't do.
Okay, so was thinking when we talked about sulfur.
Yeah, phosphate doesn't do. Even though it's like the ore.
Yeah, that's right.
And we're not the only group to have said this recently. That phosphate doesn't.
Okay, so
I would shake your hair.
much some situations below ground. Why this is just for limestone larger survive in naturally it's solved the solution before they reach the
Absolutely, except the roots are very, very slow. So it's not if you know your calcium content, it's not going to make that decision.
Experiment.
I switched to the it's also part of the science. So the smaller the more expensive it is. So if you have something so you need much higher That's right. Right now,
We just said,
infrared cameras on. The Gen Z is like pH 8. So it's acidic. Is its equilibrium water.
Yes, right, that's right.
Yeah.
That's right. So it's over. I mean, it should be. It should be.
Very slowly, yes.
My first thought on that would be that the gas exchange rate is being inhibited by essentially a thicker layer, a thicker boundary.
So that's what that term is.
Surfactants is good first thing.
I just wanted to say that I was planning to do it before, but yeah, this is you too. And I have to, I was planning to see you in the meeting later and it's cool results for the Gale project later.
Oh, I would love to see that.
But I have to pick up keys. So we'll do it some other time.
Measuring cult isotopes down core.
Yeah. We looked at the tribal calcites, and we're seeing this increase in temperature in the late Miocene, decrease in temperature in the late Miocene, which we relate to different proportions of Himalayan to river carbonates and overall decrease in so it's like when you look at modern river, like river sediments, you see, so you have Himalayan carbonates that are very high temperature, or reality is below its and then the upper end of the component is calcium coming in the river at their surface temperatures. And so increased residence time.
Oh, in the river itself, how much of the carbonate is oxygenic?
it's changing downstream.
Yeah.
It's increasing downstream.
Yeah.
And as you go like next to the mouth of the Ganges, it's like 80% or 68%. Yeah. Wow. And it used to be much less if you go to the mid or early Middle. So that's yeah. Okay.
That's very important for when we think about cation loads of rivers as a measure of filtering.
Yeah.
If there's precipitation of calcium carbonate, which you're demonstrating is going to then a lot of these budgets about zones are not right.
So I think they address my vehicle.
Yeah, it's just getting out into the literature as a possible idea.
Yeah.
But if you avoid quantifying,
Oh yeah, no, we were definitely trying that. A long time.
So what about upstream?
I mean, now it's a question of what is. I mean, some of the generated river system, it can be solid carbonate, it can be neogenic, or it can be just spontaneous.
Right, so carbonate is an issue.
Yeah,
But do you have along a whole watershed from high altitude to low altitude?
it's
Some kind of scope measurements.
Yes, we do. So in the mountainous rivers, it's dominated by the lithic component. Yeah.
Dominated like 9% or
Yeah, I mean, there's also a you get into a problem of it's not a single element component now, but you have some local variations, but it's generally hot, and then most of the contribution of the holder, carbonate is down to it downstream. It's in the floodplain.
in the flood?
Yeah.
Oh, that's very useful.
Yeah.
That might save us.
Yes.
Well, we run into contamination issues. Like, I'm thinking about Preston's work.
No, I had a really interesting chat.
Good.
So he wanted to try and measure sulfur isotopes in those secondary area, but it's like 1 or 2% of carbonates in the sediments, of which maybe half is outside.
You know what? I want to do it.